To help find the derivative of sine of x, we're going to need to find the limit as x approaches 0 of sine of x over x. We're going to do this using a method called the squeeze theorem. Now it's more of a visual proof, so let's draw it to help us understand what's going on. So I'm going to start by drawing the unit circle and drawing my x and y axes. Next, I'm going to extend the radius just past the circle and make a right angle triangle that's tangent to the edge of the circle. I'm also now going to make another triangle that's going to be isosceles from the radius here. So I now have three different shapes that I'm going to work with. I have this isosceles triangle here that I'll just color in red. I have the piece of the circle here that I will color in pink. And I have this larger blue triangle here. So now we can actually make a comparison between the areas of all of these three shapes. We can say that the area of the isosceles triangle is less than or equal to the area of the piece of the circle, which is less than or equal to the area of the larger triangle. So notice if I take the area of the isosceles triangle, add a little bit, and I get the area of the piece of the circle, and add a little bit more, and I get the area of the large triangle. So this relationship between the areas makes sense. So if you remember at the beginning, I said this was the unit circle, so I have the radius is 1. So let's find the area of the isosceles triangle. I know that the base is 1, but I need to find its height. So if I have this angle x, I also know that the hypotenuse of this right angle triangle I've made is 1, because it is also the radius of the unit circle, which then makes the opposite side sine of x. So the area of a triangle is 1/2 base times height, which means the area of this triangle is 1/2 times 1 times sine of x. So now for the area of the pink piece of the circle, the area of a sector of a circle is the angle times the radius squared over 2. So for this piece of the circle, we have x times 1 squared all over 2. Last but not least, we need the area of the blue triangle. So in this one, we know that the base is 1, and we also have this angle x as well. And the height, instead of using sine, we're going to use tan. So the height of this triangle is equal to tan of x. So again, the area of a triangle is 1/2 times base times height. So the area of the blue triangle is 1/2 times 1 times tan of x. So now let's simplify this a little bit. So we have a sine of x over 2 is less than or equal to x over 2 is less than or equal to, and I'm going to change tan of x to be sine of x over cos of x, so I have less than or equal to sine of x over 2 cos of x. Now everything has 2 in the denominator, so let's go ahead and multiply everything by 2. So it leaves us with sine of x is less than or equal to x, which is less than or equal to sine of x over cos of x. Because I have formed the triangles with the x-axis, my angle x is restricted between 0 and 90 degrees. So if I now divide everything by sine of x, I'm not dividing by a negative number, which means the direction of my inequalities does not change. So if I divide everything by sine of x, I have 1 is less than or equal to x over sine of x, which is less than or equal to 1 over cos of x. Now note how the middle of this inequality is the reciprocal of what we're trying to look for. So let's take the reciprocal of everything. When taking the reciprocal, now we need to change the direction of our inequality. So we're now going to have 1 is greater than or equal to sine of x over x, which is greater than or equal to cos of x. Now let's take the limit as x approaches 0 of everything. So we have the limit as x approaches 0 of 1, which is going to be greater than or equal to the limit as x approaches 0 of sine of x over x, which is greater than or equal to the limit as x approaches 0 of cos of x. So since there is no x in the first one, the answer is 1, which is greater than or equal to the limit as x approaches 0 of sine of x over x, which is greater than or equal to 1, because as x goes to 0, cos of x goes to 1. Note how the limit we're looking for has to be greater than or equal to 1, but also less than or equal to 1. The only possible way for this to happen is if it is equal to 1. This is why this proof follows something called the squeeze theorem. I've squeezed the limit I want in between two values. So in summary, the limit as x approaches 0 of sine of x over x is equal to 1. In fact, the limit as x approaches 0 of sine of a of x over a of x would also be equal to 1. As long as what the angle is and what the denominator is are the same, the limit will be 1.